In this video, we are going to give a brief introduction to elliptic curves and introduce an associative binary operation on them. So the first thing we're going to discuss is what is an elliptic curve. And an elliptic curve is one of the form y squared is equal to x cubed plus ax plus b, what's called a depressed cubic because it's missing that quadratic term, some sort of coefficient times an x squared. And it's going to be subject to a technical condition, which is that we want the quantity 4a cubed plus 27b squared to be a non-zero integer. The reason for this is sort of like having a discriminant of 0 when you have a quadratic equation, so we want to avoid that technicality. And elliptic curves, if you graph them, can have all sorts of different shapes, ranging from just a kind of sideways curve to these things that have little bumps to almost having this egg-like shape that's detached from a more standard curve in this sense. Now, if you go back and you take a look at the elliptic curves that we had on the previous page, if we think of all of the points in the plane and we let E denote the points in the plane that happen to be on the elliptic curve, when we have two different points, call them A and B, that lie on the curve, we can draw a line between them. And then what we can do is introduce an operation that we're going to call star, and we're going to define that A star B to be the third intersection point on the curve. So let's walk through a specific example with an elliptic curve using this star operation. So we're going to escape out of here and pull up Desmos, which is just desmos.com, some free software that you can use that's really nice for graphing things. Throughout this video, I'm going to be using the elliptic curve y squared is equal to x cubed minus x plus 1. And Desmos has graphed that elliptic curve for me right here. You'll notice that we satisfy that discriminant condition. If I look at the quantity 4a cubed plus 27b squared, I get the number 23, which is certainly not 0, so this works as an elliptic curve. And there are a handful of nice integer points on this curve, which is one of the reasons that we use it. One of the points that lies on this curve is the point 1, 1, as you can see there. Another nice point that lies on this curve is the point 3, 5. Let's just use, for our example, we're defining that star operation. Let's think of the blue point as A and the green point as B. And we can draw a line through those 2 points, and we'll see that it intersects the elliptic curve in a third spot. So if I write the equation of the line through the point 1, 1, and 3, 5, I have y minus 1 is the slope, which is 2, times the quantity x minus 1. You see that line goes straight through 1, 1, and 3, 5, and it intersects our curve in this third intersection point, which is the point 0, negative 1. So if we were looking at A star B, with this being A and this being B, A star B would be this third intersection point right here, 0, negative 1. Just to demonstrate that operation again, another nice point that lies on this curve is the point 0, 1. And we could draw another line. We could take the line in between 0, 1 and 3, 5, which has the equation y is equal to 4/3 times x plus 1. You can see that line goes through 0, 1 and our point 3, 5 that's right up here. So if this were A and this were B, then A star B would be this third intersection point right here, which Desmos is identifying as negative 1.222, negative 0.63. So that's our star operation. Now, one of your homework exercises is to explain why this operation star is actually not a binary operation on the set of points that lie on the elliptic curve. However, it's really close. It's very close to being a binary operation, so instead of shrugging our shoulders and just giving up, what we can do is make a brand new operation that this time we're going to call circle on the set of points of the elliptic curve that is a binary operation, but we actually need to add a point, and that's set theoretically, we add a point. Visually, it's more like a line, but we're going to think of it as the point at infinity to the set. So let me go back to our picture to show you what that's all about. If I go back to Desmos, what I'm going to do is I'm going to think of, as we zoom out on our elliptic curve, we want to think about infinity as also being a point on this curve. So if we ever have a situation where we draw a line between 2 points and it doesn't happen to intersect the elliptic curve in a third spot, we're just going to say, all right, let's define that third intersection point to be the point at infinity. And I'm thinking of infinity as being very high off of the graph vertically, no matter what the x point is. And I'm not thinking about it as really being signed. So I'm not thinking about this as being positive infinity and down here as being negative infinity. Both of those are just infinity, and it doesn't matter if my infinity is over here or my infinity is over here. Anything that runs off of the page in any direction is going to be considered infinity. So just to be clear on what that binary operation circle is, if we were fine in the case of star, and A star B is well defined, as it was in the first two examples that we did, that third intersection point on the line through 1, 1, and 3, 5, and that third intersection point on the line through 0, 1, and 3, 5, if it was already well defined, then don't change anything. Just think of that circle operation as being exactly the same as that star operation. However, if A star B is not well defined and you happen to find 2 points that you draw a line through and it doesn't share a third intersection point with that elliptic curve, then just define this circle operation on those 2 points to be this point infinity. So that fixes the binary operation problem on elliptic curves. However, this circle operation that we've introduced is not associative. And associativity, although not as nice as commutativity, it is a property that we want our operations to have. And so it may be technical, but we really, really wish that we had an associative operation. And just like we did with the star, this circle operation is not too far away from being an associative operation. So instead of giving up, we can just make a slight change to the definition of our operation, and everything will be working the way we want it. We'll have a binary operation that happens to be associative. So the last iteration in this process is to define one final operation, which is dot. And we're going to define A dot B to not be that third intersection point, but rather its reflection across the x-axis of the third intersection point. And again, remember that infinity, we don't really care if it's positive or negative. So if we were thinking of infinity as a very positive thing and being high in the y direction, the reflection across the x-axis would be very low. And we're not going to think of those two things as different. We're going to think of them as the same. Let's return one more time to the picture. Here I've just got the picture straight into our slides, so we can give an example of how we actually define these things. Going back to this time A being the point 3,5 and B being the point 1,1, we've already seen that if we draw a line through A and B, that we do in fact get this third intersection point with the elliptic curve. If we were dealing with the star operation, A star B would be this point that we've called C right down here. In order to make this dot operation associative, what we're going to say is that A dot B is not this third intersection point down here, but rather its reflection across the x-axis, which we're going to call negative C. We're going to think of it as the opposite of that, and that negative sign is going to stand for opposite. So the A dot B would be this point that we have identified right here on the curve. Similarly, if we were returning to Desmos, we had another example in Desmos, which was we had this line through the point 0, 1, and 3, 5 right here, that Desmos identified this point right down here, negative 1.222, negative 0.63, as being the third intersection point. We would want to reflect that across the x-axis in order to get the A dot B, where A is this 3, 5 and B is this 0, 1 point. So this point right around here, negative 1.222, positive 0.63, would be A dot B in that situation.